Yes, I certainly have. These engines are dear to my heart. I've had the privilege to fly behind and between 4 or 5 different variants of these engines, so we'll go through them in some detail and I'll point them out to you. Pratt Whitney, the dependable masterpiece. Well, that certainly is not an understatement. It's the most fascinating company, and we'll have a look at, let's just see if the slide will advance. There we go. At some of the company history, which is really something exceptional. The aero engine genesis, manufacturing of aero engines. Just to set some context in this whole development, the personalities involved, the company's firstborn, which was the 1340, known as the Wasp. Subsequent engines didn't really go into the stillborn projects. There's so much material here. The 2800, which is probably their crowning glory, and the last hurrah, which was the 4360, otherwise known as the Corn Cob. So here there were 2 machinists, Francis Pratt and Amos Whitney. They worked for various companies, but at the time they were at the Phoenix Iron Works in Hartford, Connecticut, and they founded Pratt Whitney in 1860. Some employees actually have them as former employees of Colt. These guys were actually working a day job and starting their own company at the same time. So they were pretty busy, and they had a couple of false starts, but eventually they basically was, within a couple, by the end of the decade, they'd settled down. You can see there that Amos Whitney was a distant relative of Eli Whitney of the cotton gin fame. So he definitely had engineering in his family. As you can see, the first shop burned down. As I said, a few false starts, but eventually they built up quite a decent factory in Hartford, and were pretty successful until the end of the decade. They, as I say, some histories have them as former employees of Colt, who was in that area anyway, but they made all sorts of engineering products in the late 1800s, and basically on contract. But the big thing, as you can see from the text there, they became pioneers in developing interchangeable parts. And in order to do that, you needed to build something with a great deal of accuracy. So they needed accurate gauges and standards of length, which at that stage of the Industrial Revolution was not a given. It's a little bit of research I found on them was that they made quite a lot of firearms. Being the late 1800s, there was tremendous development in the firearm field. So you can see the Lee Enfield was said to have been built at their shop. Even Mr. Mauser had some prototypes and some machining done there. And they certainly, Germany imported a lot of Pratt & Whitney gun-making machinery in the 1870s, which of course was the time of the Franco-Prussian War. And by the end of the century, the Pratt & Whitney company was purchased by the Niles Bement Pond Company, which was the start of the real corporatization of the Pratt & Whitney company. A company founded on rigid precepts of accuracy that clings unswervingly to that principle for over a century. Well, that's a pretty fair assessment of the Pratt & Whitney company. Accuracy I did touch on earlier. It's certainly the way to produce interchangeability, and the art of this was making them at a fraction of the cost of previous hand-tooled and handmade parts. At the bottom of this laid the establishment of the standard inch. Now, an inch, if you look at what an inch is, it was a whole number of barley corns put in a row, and it was the length between a man's first digit on his thumb and the thumbnail. And there was nothing standardized, so they worked out a standard inch, and they made a gauge. In other words, it's a block of metal that's been machined to an extremely accurate degree, and it's kept at a constant temperature, and then that becomes the standard for which you can make tools that measure. So with that, they basically started making measuring tools. So they financed these 2 academic gentlemen here, and they managed to build a measuring gauge which could measure to 1/50,000th of an inch. and by the 1885 they managed to do it down to 100 thousandths of an inch. So this is amazing technology, and this set the standard for many engineering companies, particularly in high precision things like firearms, where you want really good quality and accuracy, so that you could interchange things like rifle bolts. Whereas previously most machines had been filed to fit, so to speak, and nothing was interchangeable. So now we're going to look at just a little bit about the development of the radial engine. The first aero engine that was built as such was actually a radial engine, and was not built by the Wright brothers. It was built by this Stephen Balzer and eventually refined by Charles Manley for the infamous Langley Aerodrome, which was actually meant aircraft, sponsored by the Smithsonian, that was used to be launched off a houseboat in the Potomac River in Washington. So they had the world's worst airplane at the time, but certainly they had the world's best engine. And this 540 cubic inch motor was producing 50 horsepower, whereas the Wright brothers had to make do with 16 horsepower on a good day. So whereas the Wrights got their airframe correct and refined and effective, they really battled with an engine. So one wonders what would have happened if they'd had access to this engine. The Wright brothers would certainly have been flying earlier. So we said radial engine. So just to recap, the difference between a rotary and a radial engine. Over here we have on the left a rotary, and if can you see my little, there's my pointer. The crankshaft of the engine is fixed to the fuselage of the aircraft, and the cylinders rotate with the propeller on that crankshaft, which is fixed. So the engine spins with the propeller, and the whole idea behind this was to cool the engine. Cooling with an air-cooled engine is critical, and if you want to make more power, you generate more heat. And you have to do something about that heat, otherwise it will melt the engine down. So the rotary was a solution for that. It crewed, it worked, it was fine for the First World War, but it definitely wasn't going to have much application in commercial aircraft after the war. They're heavy on fuel, they're not very reliable, and they were difficult to handle in terms of engine management. So the Radial is actually very similar design internally. If you have a look over here, is this thing in the way? You've got now you have the engine that's fixed to the aircraft, and the crankshaft rotates. That's the master connecting rod with the other cylinders, all bolted onto the master rod, which then runs around the crankshaft and turns the crankshaft, which then turns the propeller. So that's basic difference in design there. We'll have a quick look. I've got some nice shots here of the rotary engine design. Because it's spinning around, you can't bolt a carburetor to it. So it's the fuel comes in from the back of the engine and into the crankcase. Like a two-stroke, it's mixed with oil. The mixture is slurried around here, and as the piston comes down, there's a valve in the crown of the piston. There's the head of the valve there, and that opens so that the fuel mixture, air fuel mixture, will come into the cylinder and then be compressed when the piston comes up, and when it fires, then the exhaust valve, which here's the push rod for the exhaust valve, the push rod and the rocker will open the exhaust valve, and it would let the gas out. So this was known as the mono soupape, which means mono valve. It's only got one valve that's operated. The other valve is automatic inside the piston crown there. Anyway, no such nonsense for the radial engine. Conventional valves. One way to cool the radial engine, one of the earliest designs, is actually a liquid cooled radial. So as you can see, the Salmson 9Z has got a crankcase, they've got cylinders. This is actually a mild steel water jacket that's been welded around the cylinder, exactly as they would do it with an inline engine, and the engine is then cooled by that. This is an exhaust ring. This cowling collecting, as you can see, the exhaust gases from each cylinder here, and then there's an outlet pipe there. As you can see here, between the cylinders is a water pipe, so that the water can circulate Not a great idea, because now you've got the large frontal area of the radial engine combined with the weight of a liquid-cooled engine, which is like a double negative. So the big advantage of a radial engine is it's air-cooled, and thereby you dispense with the water cooling system, which creates drag and weight, and you allow the air to cool it. But how to cool it effectively was the big secret here. And the first guys who really got it, call it right, was Bristol, the Bristol company. You can see the Bristol Jupiter, which was the first really successful air-cooled radial. We'll have a closer look at it here. Radials come in all shapes and sizes, but always with odd numbers of cylinders. So the most basic radial would be a 3-cylinder in this, and Zani here is a 3-cylinder. This is a cutaway of a Jupiter on the right, and you can see the push rods in the front with the rockers exposed, and that's an intake valve there, and the mixture will come into the valve, into the cylinder, and then the exhaust valve sitting here in front of it, operated by another rocker shaft, and the exhaust normally comes out to the front of the cylinder. So if you look here at this picture, you can see the exhaust valves at the front here. This design has actually got 4 valves per cylinder, so there's 2 exhaust valves on each cylinder, and then they put a collector ring around here, rather like this one here, to collect the exhaust gas. Okay, so that's the early radial design. So now let's look at America, because we're focusing on Pratt Whitney. So we'll follow the development of radial engines in America. They had the predecessor to NASA was this company, this organization called NACA, for aeronautics, and they basically came into being after the end of the First World War, and they looked at all aspects of aviation from a scientific point of view, and they definitely agreed that there's a case for air-cooled radial engines. The Navy was very interested in air-cooled radials because a radiator on an aircraft that's flying over the ocean, if the radiator springs a leak, that means the pilot is going to end up in the water. It can also suffer battle damage and the same result. There's an apocryphal quote from a US Navy admiral who said, "A water-cooled aero engine makes as much sense as an air-cooled submarine." So the US Navy said, we're only interested in air-cooled engines. And so this guy, Charles Lawrence, came up with an engine which was developed with Navy funding using aluminium cylinders with steel liners, and it ran for 300 hours, which was quite a feat at the time. So what happened was the Navy asked the Wright Aeronautical Corporation to buy Lawrence's company, and these engines were then built as under the Wright brand name. So if we have a look at this, you can see the exposed valve springs over here, and the push rods are exposed as well with the rocker, and this was one way of keeping things cool. The exhaust valve, of course, is the one that gets the hottest, and it has to transfer that heat somewhere. So by having air flowing through the rocker and the valve spring that's attached to the valve itself, it was hoped to conduct some of that heat away and not burn a valve. Very crude exhaust system here. You can see just a little stub in this case. So the Wright J5 was probably, you could call it, the first truly reliable and high power to weight ratio modern aero engine. And this particular engine was the one that powered Lindbergh's historic transatlantic flight. And there probably were no other engines at that time that would have been able to accomplish this feat, to run for that length of time at a high power setting. Part of the development now, we'll show you this gentleman by the name of Mr. Heron. He was a British expat living in the US, and he invented sodium-cooled exhaust valves. So now what they did was the valve had a hollow stem, and sodium was introduced into that hollow stem when the valve was made. Sodium has a low melting point, and it moved around inside the hollow of the valve stem so that it would pick up the heat at the face of the valve, and then transfer the heat to the end of the valve, and in that way help to cool the valve, keep the face of the valve cooler. And this allowed the Heron to enclose his rockers and enclose the valve. So you can see there's a little rocker box here now on each valve, which is better for lubrication because they could introduce oil into this rocker box, which would keep the rocker functioning, whereas an exposed rocker would eventually run dry of oil and seize. And you can see a much more sophisticated arrangement to cool the valve seat area. A lot more fins in this area here underneath the rocker box. Magnetos out here in front. Well, pros and cons to that. It does keep them cool because they're running in the cool air and they're accessible for adjustment on the ground without removing the cowlings or getting in from the back of the engine. So this was a truly landmark engine, the J5 Wright. And Charles Lawrence, the inventor, was awarded the Collier Trophy for his outstanding performance. And the Collier Trophy is like the ultimate trophy awarded annually to the person who's made the greatest contribution to aviation. So very prestigious award. Anyway, the Wright Whirlwind was used in landmark aircraft like the Ford Trimotor and the Fokker 7. But there was a gentleman by the name of Frederick Rentschler, who was working for the Wright Company. In fact, he held a senior position there and was the CEO at some time. And he became frustrated with the Wright Aeronautical Company, felt they were resting on their laurels. The investment bankers had no real interest in what they did, no vision, were not prepared to capitalize the research for bigger and better engines. And so with that, he went to see the Navy, and he had an acquaintance there from his wartime service, this Admiral Moffett, who was in charge of procurement at the US Navy in Washington. And he told Admiral Moffett that he could build a 400 to 500 horsepower air-cooled radial that weighed less than 650 pounds. Now, 400 horsepower from 650 pounds was unprecedented, and that would be the installed weight, not just the engine plus the radiators plus all the other coolant that added weight. This was an installed weight, and the Navy was very interested, but they said they had no money. It was just after the First World War, and the budgets were low. And he said, "Build it, and then if you can show us that it works, we would very much be interested in purchasing this engine." And this was the catalyst for that purchase. The Washington Naval Treaty was an early attempt at disarmament in the major naval powers of the world, and they decided to limit the tonnage of ships. Those who understand the frustration of the Japanese Navy at the time, where there was a ratio between the big navies of the world, and the Japanese got the short stick. Anyway, so the United States was building 2 heavy cruisers, and they decided that seeing that they couldn't build them now because of this naval arrangement, they would convert them to aircraft carriers. So they became the Lexington and the Saratoga. That's what happened to them. The Lexington was sunk and the Saratoga survived the war. So they weren't ideal because they were laid down as cruisers, but they certainly were effective aircraft carriers and served in the Second World War. So now that there's a demand, and he's got an arrangement with the Admiral, or an understanding with the Admiral, what did Rentschler do? So he started putting some family connections there, and through his brother, who was a banker, he heard that the Pratt Whitney machine tool company was an excellent manufacturing company. They were used to building things with a great deal of precision, and they had capital and extra factory space at hand. So he went to see the president of Niles Bement Ponds, which, if you remember, had bought Pratt & Whitney back in 1901. He was a friend of the family, and a deal was struck in July 1925, which created the Pratt & Whitney Aircraft Company, separate to the machine tool company. So the next month, Rentschler resigned, and his design team, led by George Meade, who was also from Wright era, moved into a factory that had been earlier home to the Pope Hartford Electric Automobile Company. And they'd obviously gone bust, and so they had space there, and they began to work on the Navy's engine. This is the Niles Bement Pond Company, an advert for them. As you can see here, Pratt & Whitney subsidiary Precision Machine Tools machinist, small tool standards, and gauges. So that was their stock in trade, making gauges to measure with a great deal of accuracy, as discussed earlier. So they moved into this factory, but before that, they had a little bit of experimentation in a garage. Great ideas are often done in people's garages. And these were the gentlemen who left the Wright company to come in with Rentschler and design their idea of what an aero engine should be. So Montclair's New Jersey, it's not that far from where they ended up, but once the facilities were available, they moved along there, and they moved to Hartford in Connecticut and got stuck in. On the right, we have the very first Pratt Whitney Wasp engine built, and on the left is a picture of the 1000th engine with some of the progenitors, Meade, Rentschler, Brown, and Wilhus. These were the real fathers of the Pratt Whitney engine. The first engine was a great success. There's anecdotal evidence that it was built so well, the tolerances were so fine that it wouldn't turn over, so they had to disassemble it and fudge it a little bit so that it would run. But it was an amazing motor. It produced 420 horsepower straight off the bat. So they could be very happy with it. Completed on the 24th of December, so it was a Christmas present to all concerned. This quote is from Rentschler. He says, it ran, it was clean as a hound's tooth. It was actually the thoroughbred that it looked. These characteristics had never been previously achieved in an aero engine. This is the number 12, the last of the experimental engines, which is in the Henry Ford Museum at the moment. The Navy ordered 200 of them before the 6th prototype had been built. So they just got it all. They just had it licked. They got it right from the word go. The name Wasp was suggested by Rentschler's wife. They decided that it was a pun on the noise that it made. It had a rasping sound, and it was definitely a good name for the engine. It ran on Christmas Eve, as we said, and in 1 year they'd gone from being unemployed, founding a company, and building a world-class engine. So they didn't mess around in those days. You would think things happened slowly in those days, but they certainly didn't in this case. By 1927, the government was looking at mail contracts for private airline companies, and Boeing was interested in building aircraft for this mail contract. So here on the right is a picture of Mr. Boeing and Mr. Rentschler discussing the finer points of a Wasp engine. But Rentschler eventually left Pratt & Whitney and became more involved with United Air Transport, which was a conglomerate of Boeing, Pratt & Whitney, Hamilton Standard Propellers, and United Airlines. So they basically had the whole air transport thing licked at every base. There's more of that later. In the meantime, we'll just look at things like aero engine pricing. Now, up till that point, the Curtiss D12, which was too late for the First World War, was a water-cooled V12, and this in its heyday was considered the ultimate. It was powered the Schneider Trophy Curtiss seaplanes that and it made 435 horsepower, and this was the absolute ultimate in its day. And here comes Pratt & Whitney with their Wasp. It makes more than 400 horsepower off the bat and costs less money. And in any case, the Wasp went to 550 horsepower with no further modification at all. So it was definitely the next step after the Curtiss. The Navy had been looking at Curtiss engines for their aircraft and were immediately disinterested and went straight to Pratt & Whitney's Wasp. It gave them the power they needed with a lot less weight and a lot less cost as well. Another quote from Rentschler: the best airplane could only be designed around the best engine. Now, this was a chance Vought of the Vought Aircraft Company had been battling to get an order from the Navy. He'd even gone in a tatty suit to Washington begging for an aircraft order. And he said, if you can give me an engine that can produce 350 horsepower that weighs under 650 pounds, I'll build you the best aircraft you've ever seen. And they chased him away. So here came his savior. Here was an engine that made 400 horsepower and weighed less than 650 pounds. So this was the beginning of a great deal of cooperation between Pratt Whitney and the Vought company. Just have to think of the Vought Corsair to see where this led to. Anyway, the first effort was called the O2U, O for observation, the second model, and U was the Navy's identification letter for Vought. So O2U was, you can see it on the right, powered by the first of the 1340 engines, and it was made into various amphibians as well, and seaplanes. There you can see it outside the Pratt & Whitney factory. They had their own airfield. You'll see that in the next slide. With all this ordering from the Navy, and they needed to move to a bigger premises, so that a new factory was built, a greenfield factory in East Hartford, on this 1,100-acre site, and they had an airfield adjacent to it. And that's what the picture you saw previously was named after Rentschler himself, so they called it Rentschler Field. They also expanded into Canada within a year. This is 1928, so I mean things are happening fast here. The Pratt & Whitney Canada Aircraft Company was formed, and it was initially a service center for the aircraft engines, but they started producing Wasp engines, and you can see on the right there, they're producing engines on the shop floor, and they overhauled engines, but eventually after the Second World War they focused more on jet turbines, and their most famous engine of course is the PT6 turboprop engine that's found on aircraft like King Airs and Lotus 12s. Very much the standard of the day. So let's have a look at the Wasp itself. I've just put a bewildering array of different variants here. They made nearly 35,000 of these engines. You can see they all have the R for radial. 1340 is the cubic inch, that's the size of the engine, and then you have a dash, and our dash 7, dash 8, what that means, it's odd numbers for the Army and even numbers for the Navy. So if you've got a 1340-8, then it's an engine that was built to a Navy order for a naval aircraft, and if it's an odd number, then it's an Army engine, or Air Force, Army Air Force as it became. So here's a good example. Here's the P26, the P shooter, which had a 600 horsepower version, and it was known as the Dash 33. So that engine was then specifically built for that airframe, and its exhaust system and its ignition system and everything was optimized for that airframe. Then you get the AN series, Army Navy. So this is actually one of the few times that the Army and the Navy saw eye to eye. So that variant AN1, AN2, this was actually used in the Harvard, which was used by the Navy as an SMJ and by the Air Force as an AT6. So they thought, well, it's stupid to have different contracts for engines, so they standardized on this variant of the 1340, and they called it the AN1. So that the other engine of interest here is the civilian engines. They use this nomenclature here, S1H1. Not quite sure. S, I think, is supercharged. I'm not sure what the D's and the H's are for, but the G certainly means geared. So this is where the start came with gearing. Now, we'll talk a little bit about gearing later on, but a geared engine means that the engine crankshaft is turning faster than the propeller. Basically, the reason for this is once you start turning over 2,000 RPM, the propeller tips get very close to the speed of sound. And of course, the longer the propeller, the faster the tip speed. So you becomes a bit of a compromise as to the length of the propeller. And seeing we're talking about Harvards, this particular, the Harvard engine, that rasping sound is on takeoff is the tips of the propeller getting very close to the speed of sound and actually creating a bit of a shock wave, and that's that rasping sound that you hear. So in order to get more thrust and more power, you had to gear the propeller down, and you could use a bigger, longer, slower turning propeller and run the engine at higher RPM, which would then liberate more power. But of course, then at the expense of having a gearbox. Anyway, we'll touch on that a little bit later. Here's the Boeing Model 40 mail plane that we referred to earlier. This was designed to carry the US mail, and had to be reliable, and it had to be able to climb over the Rocky Mountains. So they were built very, very robust, and they were built to carry a payload, not very fast, as you can see. But this same aircraft, when equipped with the Liberty engine, which was developed in World War I and was also around about the 400 horsepower class, 300 to 400 horsepower. A liquid-cooled V12 with separate cylinder jackets, prone to leaks, couldn't turn at a very high RPM, and weighed a lot more than the Wasp. So just taking this Wasp engine, sticking it on the same airframe, meant that the payload would increase from 700 pounds of payload to 1,800 pounds. I mean, that is a huge advance. It could carry more than double the amount of mail with enough fuel to fly the same distance. And of course, your order of your reliability of this engine, being air-cooled and not prone to water leaks, was up by an order of magnitude. If you were flying over inhospitable country, then the reliability of the Wasp was definitely a great deal of comfort to the pilot. So the Wasp then started to earn its keep with the civilian airline world. The Ford Trimotor, which had first flown with the old Wright Cyclone, not Cyclone, the J5 Wrights that we saw earlier, when it was re-engined with the Wasp, it had more power, better reliability, less weight. So that's on the left. You can see the Trimotor, the 580. That's one of the last Trimotor models. Came out with the Wasp at 420 horsepower, and also the harbinger of the future, the Boeing 247, also equipped with the Wasp engine in its early forms. And this was the real progenitor of the modern airliner. We'll touch on the Boeing 247 later. These are both hanging in the Smithsonian. The Air Force also bought Wasp engines. We did touch on the pea shooter earlier along. It used a 600 horsepower version of the Wasp. As you can see, two-bladed propeller. They're trying to streamline the engine. Now you can see they've got a very complex inner cowling over the cylinders and an outer ring. Now, this wasn't a very successful arrangement. That same organization I mentioned earlier, NACA, NACA, they had done experiments with cowlings, and they discovered that the radial engine could be cowled very neatly and closely, and the hot air that expanded inside the cowling from the engine could be channeled to flow between the cowling and the front of the fuselage there. And so once that air started flowing out there, it actually created a positive thrust. Exhausts could also be collected to provide some positive thrust. And so a lot of the advantages of the big frontal area of the radial engine were starting to be negated by scientifically designed cowlings. This was an early attempt and not as successful. They only built 150 pea shooters and were basically obsolete within 3 years.
Is that a blackbird? Sorry, is that a blackbird in the bottom left?
Yes, it is. This is in the Udvar-Hazy in Washington. Udvar-Hazy. This glider, I think, was a trainer, American glider trainer. You can see an F4U here. Look at the difference in that cowling compared to this cowling over here. The Wasp was also used to break records, aviation speed records. This is a GB R1, which used a 1340 engine. It won the Thompson Trophy pylon race, flown by the legend Jimmy Doolittle. On the same weekend, he also sent a land speed record for land planes, speed record for the fastest land plane. As you can see, the Supermarine SXB was a seaplane, so it had a much longer takeoff run and it had a much bigger, more powerful liquid-cooled engine, but it was a pure racer. This engine was basically, I won't say army surplus, but it was an engine that was in mass production and had been fitted to the pylon racer. It's a 10-mile course, the Thompson Trophy, with 50-foot high pylons marking the turns. It was held from 1929 to 1961, mostly in Cleveland. There were some races in Chicago and also in LA, and was discontinued in 1961. Then the baby brother, if you can call it that, was the R2. The R1 was number 11, and the R2 was race number 7. And this particular aircraft, I've seen it fly at Oshkosh, flown by Delmar Benjamin. He built a replica of the GB Racer, and this uses the smaller brother to the Wasp, the R985. The reason for that was its fuel consumption is slightly better, and this aircraft was built for the Bendix race, which was a cross-country race generally run between Burbank, California, and Cleveland, Ohio, also from 1931 to 1962. So it's a slightly sleeker, tapered engine cowl than the R1. It was replicated and flown by Delmar Benjamin. A lot was learned about what is myth and what is true about these aircraft. And anyway, it was retired from flying, and it's now an exhibit. Other people also broke records with the Wasp engine. The Lockheed Vega was a favorite mount of record-breaking pilots in the 1930s. This is Ruth Nichols here. She was the only woman to hold world speed, altitude, and distance records all at once. Amelia Earhart, we've all heard of. She did her transatlantic flight with it, took off from Newfoundland, and in a Wasp-powered Lockheed Vega. She was planning to fly to Paris, but she had some adverse weather and some instrument failures and ice and fog and fuel leaks. And so she decided to land when she could see the ground, and she ended up in Northern Ireland. It's still an incredible feat, distance flown. It's over 2,000 miles in just under 15 hours. The aircraft still exists. This is Amelia and her aircraft. So you can see very similar to Ruth Nichols' aircraft, and there it is on the right at the Smithsonian. The Lockheed Vega. The other pilot who liked his Lockheed Vega was Wiley Post, also a record-breaking aviator from the 1930s. He had only one eye. He had an eye patch, and he flew in a pressure suit, which he designed and built himself. And he was the first person to fly over 50,000 feet in altitude and fly on a jet stream entering the stratosphere. Solo circumnavigations of the Earth, and that was his speciality. There's the aircraft in the Smithsonian with some of its records and feats stenciled on the side. But such is the pace of progress that was once a record-breaking engine in frontline fighters, racers, records-breaking aircraft within a decade was now the standard engine for a training aircraft. Power had quadrupled at that stage, and now 550 horsepower was no longer suitable for anything other than a training aircraft. So here's a lovely photo of the Waves, which are Navy auxiliaries working on an SNJ, which is Navy for a Harvard, Navy speak, in Florida during the war. Nice old original wartime color photo. The other people that used this engine, this is a Wirraway. This was Australia's version of the Harvard. They took out a license to build this training aircraft before the US Navy and Air Force adopted the Harvard. So it's a slightly earlier design based on the NA-16 or NA-33, depending on where you look. And why I included this picture, because it's a very good shot of a geared Wasp engine. Have a look here. If you see this part of the crankcase here is actually the gearbox. It's got strengthening ribs because there's an epicyclic gear in here, and you'll notice it's got a 3-bladed propeller. So this engine could turn at a slightly higher RPM than the engine in the Harvard, but the propeller was turning at a more efficient, lower airspeed, lower rotational speed, should I say. A more efficient prop having 3 blades. So the Wirraway would have had slightly more power and significantly more thrust than its Harvard stablemate. So pictures are taken in Perth at Jandakot. So eventually in 2016, this engine received the accolade it deserved all along. It was considered a landmark, historic engineering landmark from the American Society of Mechanical Engineers. So we can do, from this, we can have a look at some of the significant improvements over the Wright engines. The engineers at Pratt Whitney decided to have a single piece master connecting rod. instead of one that was made up of 2 or 3 pieces, and that allowed the engine to be much stronger and allowed it to turn at a higher RPM. So in order to fit this now onto the crankshaft, they had to build the crankshaft out of 2 or 3 pieces. In other words, it was a split crankshaft so that they could fit the master rod over the crankshaft. You've probably all heard of a billet crankshaft where it's machined from a single billet. Well, then you've got to have the connecting rods would have to be split like they are on most motor cars. In this case, the crankshaft was split and fitted over the connecting rod, the master connecting rod. The other innovation was a forged crankcase. So here your crankcase, a forged crankcase compared to the cast crankcase of the Wright engines meant that it was stronger and it could be made lighter. So because the crankcase is a significant part of the weight of the engine, a lighter crankcase means you can build a bigger engine in terms of capacity and therefore get more power. The crankcase was made in 2 identical halves, which makes sense because it means that you can reduce the complexity and it's easier to manufacture. So another typical Pratt Whitney philosophy that came out. So these 3 things were the real game changers in radial engine design, and they were only really acknowledged in 2016. So after the war, the 1340 was still in production, and it found applications which couldn't have been dreamt of back when 1925, when Wilchus and them were busy experimenting with it in their garage. Here it is in the nose of a helicopter, the S-55 Sikorsky helicopter, which was known as an H-19. It's driving a shaft that goes up between the pilots and up to the rotor. Helicopters hadn't even been thought of in 1925. And they're still earning their keep today. This is a Grumman AgCat, which was a standard crop spraying plane in the 60s and 70s until more advanced types came out. And this particular one has been modified to go on floats. They built a cockpit where the old insecticide hopper was, and passengers can go joyriding. This is the Swan River in Perth. So it's still earning its keep as a joyriding recreational aircraft. So that brings us to the end of the Wasp. Now we're going to look at its big brother, the Hornet, 1690. So 1340 cubic inches versus 1690. So it's just a Wasp engine that's been upscaled. It wasn't made in anything like the numbers of the Wasp. First flew in 1927. They were developed almost in parallel. Also a 9-cylinder engine, 27 liters. But where it really becomes significant, this was widely copied. In Italy, Fiat got a license to build the Hornet, and particularly in Germany, the BMW 132 was a developed version of this aeroplane. I mean, they built over 21,000 BMW engines, considering they had to put 3 at a time on a Junkers 52. And the Germans developed it, they geared it, and they managed to get, in some versions, up to 1,000 horsepower, which is pretty impressive, considering it was really typically a 700 horsepower engine. There was a bigger brother called the 1860 Hornet B. I've got one picture of that. That's a particularly rare engine. And the other version of the Hornet was the Enma Beta. Now this has some significance because Enma is a Spanish company, and so that's the licensed version of the BMW, which is the licensed version of the Hornet. And the SAA Junkers 52, when it was delivered here, it's actually a Casa 352, came with these Beta engines. And SAA found them, they couldn't get parts for them, they couldn't get manuals for them, and so they made a plan, and I'll show you that later. So that's the Hornet. This is just a quick run from Wikipedia for the different variations. Once again, odd numbers for the Army. These are the civilian ones. G, that's a geared version to get more horsepower. These are some of the aircraft that it was used in. Many of them were just prototypes. And like the very first Focke-Wulf Condor came out with these engines until the BMW engines were ready. Junkers 86 South African Airways had Junkers 86 airliners, and they were Hornet powered. So it was the Junkers 52 Hornet powered. The early Lockheed Electras, and some of these, as I say, are very obscure aircraft. But here's a significant user of the Hornet. Boeing's first passenger airliner from 1928 had 3 Hornet engines, 12 passengers, and 1 female flight attendant. So they set the pattern for airliners going forward, and this is the great granddad of all the Boeings that came after that. It's also the engine of choice for the golden age of civil airliners. The Lockheed 14 Super Electra came out with Hornets, and the Sikorsky S-40 flying boat. But eventually, many of these aircraft were re-engined with more powerful Pratt Whitney engines like the 1830, and that's why that didn't make so many Hornets. It was actually a bit of an interim engine. The horsepower race was on, and modern aircraft wanted more power in order to go faster. And many were upgraded with either the Wright Cyclone or the 1830. So here's our Junkers. I did some research on the original Ju-52s that were delivered to SAA back in the 30s, and they were called the 3M-SA1. Was the variant sold to SAA, and they had the Hornet 650 horsepower Hornet S1EG, so supercharged with a gearbox, and you can still see here on the front of the engine that you can see the gearbox with the ribs to strengthen the gearbox. Now, at the time, the Swedes were ordering these aircraft, a Swedish airline, and the Swedish airline preferred geared Wasps, and they thought they were more economical and almost as powerful, and they aligned the engines. The outer engines of the Junkers are splayed slightly outwards, and the Swedes decided they would prefer the engines basically aligned with the direction of flight. And as you can see, that's this aircraft, Henry Pottinger, was built along those lines with the slightly angled engines. They were angled to align with the direction of flight. And look at the cowlings on these engines. They're much more like the Necker type cowling, much more efficient cowlings, wheel spats to reduce drag. So this, to me, here is probably the ultimate Junkers for airline purposes, with the streamlining, the better cowlings, and the geared engines. So when the Junkers arrived at SAA workshops in the 1980s for the 70th anniversary of SAA, the Enma Beta engines were removed, and they acquired 3 1340 AN1 engines from the Harvard, from the Air Force. And they were fitted, and they proved pretty successful with their reliability. 2-bladed props, it was a little bit down on power compared to the Hornets and the BMW engines, but it was fine for the purposes that it was utilized, and it made a lot more noise. 2-bladed props, the distinctive sound, it sounded like 3 Harvards flying in close formation. Here's the Hornet B, the only reference I could find to a Hornet B, so slightly bigger, 1690 cubic inches. Made very few of these. They increased the bore by 1/8 of an inch and the stroke by 3/8 to give more capacity, and it powered these rather obscure aircraft. There's one that's mounted on a service stand with its serial number, Hornet B. But before we go bigger and better, because that's why the Hornet story is fairly short, we'll go smaller, and we'll have a look at the Wasp Junior. So this is the baby brother to 1340 Wasp, run in first time in 1929. They just use smaller cylinders, but many of the parts are interchangeable, and particularly the mounting, so that an aircraft can be up-engined from this to the 1340 if so desired. The advantage of this engine is a slightly smaller diameter, lower weight, better fuel consumption for aircraft types that, 550 plus horsepower is too much. So typically they produced 450 horsepower. That's the most common version of it. So what did they fly in? Well, here's a confusing looking airplane. People would think it's a Harvard, but it's not. It's a Yale. The Yale was another North American design with fixed undercarriage, and it was ordered by the French Air Force and Navy as a training plane. So some of these ended up in the hands of the Luftwaffe. But they were also used in Canada, and the British also took over some of the Yale orders that the French had ordered, and then France capitulated. There's quite a lot of aircraft that fell into that category. So this one here was built in Dallas, but quite an interesting view here on the right of the exhaust system that's unique to this engine. The exhaust is in the front. You can see the collector ring for the exhaust is around the front, and there's a very long exhaust pipe down the side, which tells me that this was built for the Canadians, or utilized by them, because it's pretty cold in Canada in winter, and this long exhaust pipe has a jacket around it so that air can be passed over the exhaust and then ducted into the cockpit to keep the pilots warm. Other uses of the 985 was the Vultee Valiant. So this was part of the US Air Force training, step-up training process. The pilots would be selected, and some given initial training on the Piper Cub under a civilian tutorship. And then they went on to the Stearman. The Stearman, a 220 horsepower biplane. And if they passed that section of the course, they were moved on to the Valiant. So here they had still they had fixed gear, but it was a monoplane with a variable pitch propeller. So they were getting the next sort of step up in the system. And then finally they went on to Harvard 86 SNJ in the Navy, which had a retractable undercarriage and 550 horsepower. So this 985 Radial really fitted in quite nicely in the whole scheme of things there. Here's the Kingfisher, the Vought Kingfisher observation plane that carried on American warships for reconnaissance, also used the 985 Radial engine. Another aircraft that made extensive use was the Beech Model 18, a classic late 30s twin engine private type aircraft. They produced over 9,000. They were used in the Second World War in many roles. C-45 would have been a transport aircraft. The AT-7 Navigator is a training aircraft for training bombardiers. It had a glass nose, and the bombardier trainee would lie in the nose. So it was a variant of that. AT Advanced Trainer, and there's that's another version of the Navigator Trainer. In the Navy, it was an SNB, which was also a training aircraft. So everything from an admiral's barge to training bombardiers and gunners, powered by the 985. These aircraft, many of them survived the war and were used as civilian hands and are flying today. Also, some of the golden age of 1930s, what they call the vintage era. This is a Howard DGA. There's one at Stellenbosch that's green, light green and dark green. I took these pictures at Oshkosh. On the right, the Spartan Executive, classic polished low-wing monoplane, tractable gear. This was the ultimate in private aviation at the end of the 1930s. And the other great user of the 985, of course, is the de Havilland Beaver, designed and built in Canada just after the war. It's the quintessential bush plane. Obviously, they had versions on floats. That was taken on Lake Winnebago near Oshkosh. A large number of them were built for the US Army for the Korean War. There was nothing being produced in America that fitted the bill, and this aircraft did everything just the way they wanted it. So it was very unusual for the US military to order a Canadian-built plane, but there you go. So nearly half the production run of these aircraft were built for the US military. Many of them are still flying. You can go for a flight in one of these in Vancouver Harbor. So very popular aircraft, and the Wasp Junior was built until 1953. Basically was the go-to engine in the 450 horsepower class. The flat six Lycomings and Continentals just couldn't produce that sort of power until turbocharging and bigger engines came along. I made over 39,000 of the R985. How are we doing for time? Another 20 minutes before we break. Okay, so let's look at the twin Wasp Junior. This was now the next step. This is a double row radial. It's a 14 cylinder, so it's got 2 rows of 7. And Pratt Whitney cobbled up this engine by using the cylinders of the 985 of the Junior Wasp. So they put 14 cylinders in 2 rows, and they came up with 1535 cubic inches. And this was the next sort of step up. 700 horsepower, could up to 950 eventually, and running at 2,500 RPM. So this means it was geared. There were geared and ungeared versions, but the geared version was the go-to engine because you could get more power out of it. It was a little heavier, but it could run at a higher RPM and drive a 3-bladed prop of a large diameter. It was a little bit of an in-between engine because bigger and more powerful engines were coming along, but it certainly proved its point. One of the aircraft it was used in was the Vought Vindicator, of which more anon, but another famous user of its engine was Howard Hughes. Because of its small diameter, relatively small diameter of 7 cylinders, it meant that it could be very tightly cowled, and it was an ideal engine for a speed record. Now, we remember that GB Racer had just scraped 300 miles per hour in 1931, I think it was 31 or 32 now. 4 years later, not even, another 50 miles an hour added to the record. Definitely an improvement. Howard Hughes, a bit of a controversial character. I don't think he was the best pilot that ever lived. And I think he got an airlock in the fuel here, and he crashed the aircraft because he wasn't paying attention to his fuel management. Anyway, it was rebuilt, and he had 2 sets of wings. It's quite interesting. He had a long span wing for the transcontinental record, and that was the record that was stood at the end of the 1930s. It was only broken after the war in a souped-up Mustang, B-51 Mustang. And there is the aircraft in the Smithsonian, the actual Howard Hughes H1 Racer. This was a military application of this engine, the Vought Vindicator. Some of them were actually ordered by the by the French Navy. The aircraft was shown at an expo in Paris in the late 1930s, and the French ordered them for their navy. SB means a dive bomber or scout bomber, and they were actually employed by the French in the Second World War with the German invasion on the 10th of May. And if you think the ferry battles were decimated trying to bomb bridges, these guys had an equally a rough time. 7 of them shot down from one squadron in one attack. Must have been pretty disheartening for the French. Anyway, when France fell, the remaining aircraft were diverted to the British, and they called it the Chesapeake. Inevitably, it was corrupted to cheesecake. The Royal Navy wasn't very enamored with this aircraft. They felt it was underpowered, and they didn't really find a use for it, so they became a bit of a general hack, towing targets and used as a trainer. There's only one left, and that's it there at the Naval Museum in Pensacola. So at this point, we're going to have a look at what I call the Boeing debacle. Now, this has nothing to do with the debacle that Boeing currently faces. The Boeing designers produced the Boeing 247, which I showed you earlier, and I said it was the first really modern airliner, which indeed it was. But it was the wrong aeroplane. Apparently, United Airways, their pilots thought it was a bit difficult to handle, and because of its size and its landing speed, it wasn't a biplane, and so they remember now Rentschler had moved across to this conglomerate to be the CEO of all these conglomerates, and he ordered the aircraft to be scaled back. In other words, scaled down a bit. So the aircraft came out, and it was actually too small, but it was well received because it was so modern. And TWA wanted to buy these aircraft, and they couldn't buy them because they were being built for United, which was part of the conglomerate, Pratt Whitney, Hamilton, Standard, and Boeing. And so TWA went across to Douglas and said, can you build a competitor, which Douglas did, but they built a bigger aircraft with a wider body. And they stuck the Curtiss-Wright Cyclone engine onto it. And this Cyclone was more powerful than the Hornet. So they ended up with a better airplane. And so there was United, who now suddenly wanted DC-2s because they were unhappy with the Boeing 247s. But I must remember that they, of course, now had to buy, not Boeing, they had to go to Douglas, and Douglas was involved with Wright. And Pratt & Whitney didn't have an engine to compete with the Wright Cyclone. So Pratt & Whitney and Boeing found themselves out in the cold, and everybody else was piling into buying the DC-2 and the DC-3. So this formidable monopoly of Boeing and Pratt & Whitney was under threat. So what saved them? Well, they were saved by the war. Franklin Roosevelt realized that the war was coming and that America could manufacture arms initially for sale to what eventually became the Allies. And he said that the American industry should ramp up to 50,000 military aircraft a year. So Pratt & Whitney expanded exponentially, and they also got subcontractors like Ford and Buick car guys to come in on the process. I'll talk a bit more about that later. The innovations continued, and the horsepower race went into overdrive. Power outputs had tripled by the end of the war, and Pratt & Whitney ended up producing a grand total of 363,000 aircraft engines for the military, which is more than half the total number of engines employed by the Allied Air Forces. I mean, that is a significant number. By comparison, BMW made only 22,000 of the 132 Radial. That's a really serious number. And what was that engine? Well, here it is, the twin Wasp R1830. So building on the experience of the little Junior Wasp we looked at earlier, the 1830 was built to rival the Wright Cyclone in the 1,000 horsepower class. That was becoming the go-to standard, 1,000 horsepower, whereas 550, 600 had been plenty. Now they wanted 1,000 and more. So this was the most numerous of all Pratt & Whitney designs, was the 1830. We can see from the picture, it's also a double row 14-cylinder engine. This, as another view, this I took at the SAA Museum at Rand Airport. This was a cutaway engine for the training of the apprentices, and it shows some of the features of the engines quite nicely. There's your constant speed unit on the propeller. Here's the gearbox for the propeller. So the input comes onto this gear. Then you've got a ring with little idler gears in between, and then you've got another gear ring there. So this gear is turning faster than that gear, thanks to the reduction of these intermediate gears. You can see that the crankshaft now has got two throws, one throw for each bank of cylinders. Exhaust coming out to the back, intake. There's the supercharger. You can see the fins of the centrifugal supercharger there, and then the supercharger blows the air into this black pipe, which is the intake pipe, and there it goes into the engine, the intake valve, and then out through the exhaust. Magnetos mounted on the front of the engine, getting their timing from the front of the crankshaft. And this is the toolkit for the engine. This is what your average flight engineer would have to carry with him, because these are the special tools required for maintaining this engine and setting things like valve clearances and operating and tensioning the nuts and bolts that hold it together. So yes, definitely the engine that saved Pratt Whitney. 1930. It started in 1930. It took a while before it came out. The first aircraft that used it was the Martin 130, the China Clipper, that inaugurated the Trans-Pacific commercial operations in 1935. It was still pretty experimental there. Not many airliners had 1,000 horsepower engines. United Airlines, as we mentioned, was now forced to buy Douglas DC-3s. Boeing didn't have a competitor for it, but being part of this UAT conglomerate, they installed the Pratt & Whitney engines on their DC-3s. So you could order your DC-3 with a Cyclone engine if you were TWA or United. You had to put Pratt & Whitney engines on. And they built 173,000 of all versions of the twin Wasp engine. And one of the reasons they built so many is because they were used on the B-24s, and that was built in huge quantities. So for an engine of its size, this is the leading production figure for a large piston engine airplane. Some lovely pics of the Martin Clipper, the China Clipper. They 3 for Pan Am in 1935. They introduced their island hopping service all the way to Hong Kong from San Francisco. It was bigger than the Sikorsky 542 and smaller than the Boeing Clipper, the Boeing 314. It was in between size, but some wonderful old travel posters alluring to the age of sail. So let's have a look at the Twin Wasp now versus the Cyclone, because they're very different engines but in the same class. On the left here we have the 1830 with a diameter of 1.2 meters, and on the right the 1820 Cyclone, which is another 20 centimeters bigger diameter. So that's the advantage of the double row engine. Less cylinders per bank, but more cylinders overall. So therefore it would be slightly heavier. There you can see the weight, 570 versus not a lot heavier, you would think, but remember Pratt & Whitney had all sorts of innovations to save weight with their forged crankcases, whereas Wright tended to be a little more backward with cast crankcases, which were heavier. So these were the deadly rivals of the day. And as I mentioned earlier, you could find them on the DC-3 variants. Here on the left is the military C-47, and basically all military C-47s had the Pratt & Whitney 1830, the 14-cylinder. So you can see, look at the length of that cowling. It's got a double row of cylinders because the cowling is much deeper. Whereas here on the right, this American Airlines DC-3 is a civilian airliner, built as a civilian airliner, not converted to one after the war from a C-47. And if you look at that cowling, look how short that cowling is. That's because there's only one row of cylinders there, because it's a Cyclone-powered aircraft. So let's have a look at the Navy, because they were the big users of these engines as well. The 1830 versus the Cyclone. The F4F, the Hellcat, the Wildcat. The Wildcat, certain models used the 1830, and other models, particularly the Wildcats that were built by Goodyear, the FM1 and 2, they used the 1820. TBD, Devastator, the torpedo bomber that was used at Midway, was an 1830, powered by an 1830. So was the R4D, which is just Navy speak for a C-47 Dakota. And of course, the famous PBY, the Catalina, that was powered by 1830s. Whereas over on the other side, the Cyclones powered the Dauntless, the SPD, and the Helldiver, Curtiss Helldiver. This is the biplane that was before the war. The Brewster Buffalo, R4D2 is a C-53, which is a cyclone-powered DC-3. So the Navy also had cyclone engines in their Dakotas. Not many, but that was available. The J2F, the Duck, was also a cyclone engine, and as I mentioned, the Goodyear built Wildcats. Looking at the Wildcat again, a lot of conflicting interest and difficult to research, but the 1830, so the double row engine, if you look at this Wildcat, it's got a double row engine on it, and it's apparently the F4, F3A, and particularly the Dash 4, Wildcat, the Dash 4, and the Martlets, the British Martlet 2 and 3B. They were powered by Pratt Whitney, and the Wright Cyclone, here's a good example of that. The Martlets that were built for the UK, also for the French, and particularly the Goodyear built aircraft, the FM1 and 2. So very much head-to-head competitors. There's just some more pictures of the 1830, showing the exhaust detail, how all the exhausts came together. Here's another cutaway. So normally the magnetos were mounted at the back, but these models, the Dash 75 and the Dash 94, had, for some obscure reason, they had their magnetos mounted in the front. So they certainly had their variations. Okay, so this is an early version of the 1830, the Dash 64. What does that mean? It's an even number. It's used by the Navy. So here we have an engine that they found complete in a crate. It was probably a replacement engine that was, crated and forgotten in some warehouse. If you read the blurb there, it says this engine could even be a zero-time motor. There's no damage, no rust. It's a time warp engine. So it comes as a quick exchange kit. So it's got its engine mount, the firewall, exhaust system, everything's there. So the idea was that if an engine was no good, they would break open the crate, pick it up with a block and tackle, swing it out in the hangar deck of the aircraft carrier, do a quick change, and it could be done within hours instead of trying to overhaul the engine in situ. This actual engine is for sale. Anybody is really interested. As I mentioned earlier, this is now the TBD. If you've got the SPD, which is the Dauntless, would have had a Cyclone. So now a Navy ship, a Navy carrier would have had to have parts for both engines, both the Wright engines and the Pratt & Whitney engines. And I guess the mechanics were trained specifically on one type or the other. And I guess there was a fair amount of rivalry between the guys below decks. So how did they build so many 1830s? Well, here's just one of the subcontractors, which is close to my heart, the Buick division of General Motors, and they built these in a special government-owned plant. Here's the picture of the aviation engine plant, and this was one of the adverts for Saturday Evening Post or one of those magazines. Buy more war bonds, and Buick powers the Liberator. So Buick always used to have a wonderful advertising slogan: when better cars are built, Buick will build them. So I suppose when better aero engines are built, Buick will build them. So they built 71,000, nearly 72,000 of these engines in this factory, which was built by the government and owned by them, which you saw on the previous slide, in Melrose Park, Illinois, just to the west of Chicago. And they were built exclusively for the B-24s. And eventually they got contracts to build for the C-47 as well. And so here's a Buick built engine on the right. They used to have this beautiful enamel badge here on the gearbox. On the Harvard engine, it was down at the bottom here, and they were generally stolen by mechanics and made into belt buckles. Here's another cutaway of the 1830, you can see the supercharger casing here. There are the vanes of the supercharger. Here your magnetos are, generator, everything here at the back of the engine. That's the carburetor there, sucking the in through the supercharger, and then it goes through the intake over there, and that's the exhaust port over there. Here's your gearbox. And of course on the B-24 they were turbocharged. Buick also built a lot of subcomponents as well. They built over 3.2 million cylinder heads. There you can see the cylinder head is made of aluminium, cast aluminium. Look at the fins carefully. When I talk about the 2800, you'll see the difference. The fins cast in aluminium, and then your rocker boxes cast in aluminium. So they had plenty of spares, which Buick was literally churning them out. And the experience that Buick got in casting these aluminium parts for the Pratt Whitney engines gave them the confidence to build an aluminium V8 for production. It's a 1962 Buick Special, came with a 215 cubic inch aluminium V8, which the bean counters at General Motors discontinued a few years later, and then they sold the whole production facility to Rover in England, and that's the engine that you get in the Range Rover and the Rover cars. It's been discontinued now, but it became a legend long after General Motors had said goodbye to it. Looking at the 1830s, I mentioned the PBY, the Catalina. This picture I took in a museum in Perth, Australia, and just to show you the sheer power and endurance of these engines. The Australians ran a service basically to carry essential mail and sometimes essential personnel from Perth to Ceylon. They took off at night. When I say night, I mean before sunrise, in the early hours of the morning, from the water of Swan River in Perth. Now I showed you that float plane AVIATION, the red one on the water. That's the same piece of water. And they would get airborne, and the sun would come up, and they would fly until the sun set, and they'd land after sunrise the following day on Lake Kogala in Ceylon, now known as Sri Lanka. And they did this whole thing at 99 knots. Wasn't a very speedy aeroplane. And they used to apparently lean the engines off so that they would burn less than 200 liters an hour. Well, the DAC was 90 gallons an hour, it's US gallons. So 45 is divided by 3.9 times 3.9 is just under like 180 liters. So amazing endurance. They hold the record for the longest duration scheduled airline service, 32 hours. I think you were pretty deaf after 32 hours of listening to those engines. How they supplied them with oil, I don't know, because the oil tank wouldn't have been big enough to. I know they had extra fuel tanks installed in the hull, but they would have had to have some way of pumping oil up to the engines to keep them running. But you know, that's quite something. Those engines ran routinely for 32 hours at cruise power settings. Anyway, the people who flew on this aircraft were given a certificate, which was called the Sacred Order of the Double Sunrise. But they were not allowed to show it to anybody because the service was kept top secret, because it flew through at night parts of territory that were under the control of the Japanese. So unfortunately, none were ever shot down. And that's just a fascinating aside for these engines. Carl, shall we break now?
John, I think, okay, it's just past 9.
Yep.
All right, 10 past 9. So,
Perfect.
yeah, all right, everybody, take a break, just stretch your legs.